All right, we got all the difference functions built in. So those that were defined as simple sums of previous values plus changes. Now we need to get the changes written in there. So this is the part where, you know, a simulation either gets real or gets weird. Some of these are simple. So the ones that we wrote down before as we were designing this, the number of people that recover, we based around a reported recovery time of an average of 18 days. What that would suggest is that 1/18th of the infected people would recover on any given day. Also, a death rate is just a number of people that are infected times a assumed, in this case, death rate, or mortality rate, M. In the model that we designed up here, there was just one death column, but we recognized that outcomes depend on whether people get ICU treatment, so we tried to include that. Also, the more complicated one is the transmission rate, which we'll return to in a bit. But let's write the simple ones. The number of people that recover. Very simple, equals the number of people who are infected times a base recovery rate, which we have as a presumed 1/18th. So rather than times 18, we're actually going to make it be divided by the mean recovery time. So that turns it into a people per day unit. Again, things in the B column are parameters. Done. So then 0.5 people would recover on first day. Now that doesn't make any sense because people aren't fractional. So this is another one of those things where when we have a rate, it's a number between 0 and 1, or a probability, it's between 0 and 1. But we want an integer number of people, so we want to put all of the calculation inside of the integer function so that you get, actually on the first day, 0 people recovered. And that actually makes sense. We're going to do the same thing with the death rate, except we have two different death rates, or different death probabilities. So the dead in the ICU is just going to be equal to the number of people who have severe case in ICU times the relative probability of those people experiencing mortality. So mortality if ICU available is B12. Those are absolute references. And recognizing the problem that we had before, we'll actually just jump right in and put the integer function in there. Number of dead who didn't have ICU treatment. This is equal integer of the number of people who have unmet ICU need times a mortality probability for them of B13, and we'll make that absolute, and done. So all the simple ones are finished. This can be copied from one day to the next. These can be copied from one day to the next because there's nothing different from one line to the next in there. And the number of people who get infected, if we return to the whiteboard, this was equal to the number of people who can get it times a probability. That's a number between 0 and 1. And that probability, we said, has to depend on the fraction of people who have the disease right now, not the total number, but the fraction. So the probability that a non-infected person runs into an infected person. That's a product of those two. So that gives us a probability that somebody they run into is infected. And then what epidemiologists would call R0, the base transmission rate, or the base infection rate, the number of people per day that get infected when there's one infected person in the population. So this is a susceptible population times the infected population divided by the total times the transmission probability that we've already put in as an adjustable parameter. So this is going to be equal to the susceptible population times the infected population divided by the total number of people. And that's not the susceptible population, it's this initial number over here, times an infectivity, or an R0 transmission rate. And that was the number that we had over here in B6. Now there's actually two parameters in this. There's the number, the size of the population. So when there's 10 people infected among 500,000, There's a lower probability of getting infected than if there were 10 people in a population of 5,000, because your likelihood of running into somebody who's infected is just a lot higher if the population size is smaller. And there's a base transmission rate. So if we look back up in the equation bar, everything with the B is a parameter, so we make those all absolutes. And then, same thing as before, this needs to be an integer. And when it's an integer, we see that 10 infected people generate 10 new infections on day 1, 20 infected people generate 21 infections on day 2, and with all of that in place, we can rip this entire line, which is now constructed with all the change functions and the increment functions, and simply copy it literally to every day in the table. So this does the time step out through 140 days, and already we have a number, 15,500 people dead with the parameters that and initial values that we set up. Now that doesn't mean that that's what's going to happen, but it means that that's what this particular run of the model says. I added the parameter, or not a parameter, but an output value up here. So the 140-day mortality rate is the ratio between the final number of dead individuals and the total population. So this says T146, that's the number that we just pointed to way down the right-hand corner. That's the last number in the deceased column. And B17, which is the total population. So it's basically the fraction of the population that doesn't make it. And in the next one, in part 9, we jump into making predictions from these, changing parameters, drawing a graph to show how everything works. And so that one should still be valid, and this one will slot right in between.